let's look at a few examples. So each one of these examples has a similar example in the previous chapter. Okay. So we start out with this example where xn is a to the power n times u of n. Right, so this is a one-sided decaying or increasing geometric series. Okay. So in this case, the z transform by the formula given before is xn, which is a to the power n u of n, times z to the minus n for n from minus infinity to infinity. Okay? Now, un here is the unit step function, which is non-zero only for n greater or equal to 0. So you can limit the summation now from 0 to infinity of, so from 0 to infinity of an times z to the minus n, okay? But we can combine these two to get a z to the minus 1, the whole thing to power n. Okay. Now this is the sum of a geometric series with n going to infinity. Okay. So for this geometric series to converge, we need, okay. So for this geometric series to converge, we need this value, a times z to the power minus 1, to be less than 1, right? To have a magnitude that is less than 1. Okay. So we need a z to the minus 1 less than 1. And this corresponds to z greater than a. Okay? So assuming that this condition holds, right, then we can apply the formula for the summation of a geometric series. So then xz is equal to 1 over 1 minus a z to the power minus 1, okay? And if you multiply both the numerator and denominator by z, you get z over z minus a, right? And this is for a region of convergence corresponding to the absolute value of z greater than a. Okay. So this here, right? This here corresponds to values of z that are, that have a magnitude greater than a. Okay. So this corresponds to all points. This corresponds to all points beyond the circle with radius a. Okay? So this region of convergence is the exterior of circle with radius a. Okay? All right. So in the continuous time case, right, when we looked at this single-sided decaying exponential, right, our region of convergence is to the right of some value, okay, on the real, to the right of some value on the real axis, okay? But for the discrete time case, the region of convergence is the exterior to some circle with radius a. All right? Now, if you observe this, you will see that this transform here has a 0 at z equal to 0 and a pole at z equal to a. All right. So if you can also plot this, okay, on this imaginary on the z plane here, right? So I have a 0 at the origin, and I have a pole at a. Okay. So similar to before, the region of convergence is bounded. We'll see later. We'll have a similar property later as well. But you can see right now that the region of convergence is either an exterior or interior of a circle that is bounded by the pole. Okay? Right. And because this region of convergence includes the unit circle, which corresponds to the discrete time Fourier transform, therefore, by observing this region of convergence, you can observe that the Fourier transform exists in this case. Okay. Well, actually, I don't think this is very accurate because in this case, a can actually be greater than 1, right? So if a is greater than 1, then your region of convergence actually does not include the unit circle, okay? So I should say this Fourier transform exists only when a is less than 1, okay? So Fourier transform exists only when a is less than 1, so that the region of convergence would include this unit circle, okay? And this is reasonable because only when a is less than 1 will this geometric series actually converge, right? Otherwise, this will blow up to infinity. Okay? Right. So we had a, in a continuous time case, we had a we had an exponential to the right, and here we have a geometric series to the right, and we could also have a geometric series to the left, going to the left. Okay. So in that case, you can write it as this minus a to the power n times u of minus n minus 1. Okay, so if you look at this unit step function of minus n minus 1, you will see that it is non-zero only for n that is less or equal to minus 1. Okay. So you can also try to find the z transform for this. This is the summation n from minus infinity to infinity minus a to the power n u minus n minus 1. Okay? So the unit step function limits this summation for n from minus infinity up to minus 1 minus a to the power n z to the minus n. 懂了？哦，少写一个 z， 好，谢谢。OK， 谢谢。All right. So we could have computed this directly, but I think we were more accustomed to have a summation, going to the towards the positive axis. So let's just do a change of variable where we change n to minus n, so that now the summation goes from 1 to infinity of a to the minus 1 z to the power n. Okay? So this thing converges if a inverse z is less than 1, in which case z is less than a. Okay? So the z transform now exists when z has a magnitude less than the magnitude of a. Okay? So if you look at this region on the z plane, this corresponds to the interior of a circle with radius a. Okay? All right? So if we continue to solve this, this will give us minus a to the minus 1 times z over 1 minus a to the minus 1 times z. And this converges for z, absolute value of z less than a. Okay. Now I can multiply both numerator and denominator by a, so I get z here, and I get a minus z, and I can flip it around because of this minus sign. So eventually, I get z over z minus a for regions of convergence that is in the interior of the circle with radius a. Okay? So again, you see that there is a circle, there is this 0 at the origin and a pole at A, but now the region of convergence is the interior. Okay? Okay. Now let's look at another example. Okay. So here, suppose that we have sum of two geometric series. Okay. So we have 7 times something that is in the form of example 10.1. And here we have 6 times something that is also in the form of example 10.1. Okay. So by applying example 10.1, we get directly the z transform, which is 7 times z over z minus 1 over 3 minus 6 times z over z minus 1/2. Okay? And the region of convergence for this first term is z, absolute value of z greater than 1 over 3. And this has region of convergence that is the absolute value of z greater than 1/2. Okay. Now, if you want both of these terms to hold, you need to have a region of convergence that is the intersection of both of these. Okay. So 1 over 3 is smaller than 1/2, so the intersection just gives you this exterior greater than 1/2. Okay. So the region of convergence, right, is the exterior of a circle with radius 1/2. Okay. Now you can combine the two terms together. You get z times z minus 3 over 2 over z minus 1 over 3, z minus 1 over 2, and the region of convergence overall is z, the absolute value of z greater than 1/2. Okay. So if you look at this form, you will see that there are 2 zeros and 2 poles. 1 0 at 0, 1 0 at 3 over 2. All right, so I have a 0 at the origin and a 0 at 3 over 2. And 2 poles, one at 1 over 3 and one at 1/2. All right, one at 1/2, one at 1 over 3. Okay. Okay. So you can sort of see that, we have a lot of similar properties as in the continuous time case. Okay. So indeed, we can go through, these properties one by one. Okay. So first of all, right, property 1 says that the ROC of this Z transform consists of a ring in a Z plane centered about the origin. Okay. So your region of convergence should consist of these rings, okay, centered at the origin. And the reason is that the convergence of this Z transform depends only on the magnitude of Z and not on the face, okay? So if you have a point that converges, then all points with the same magnitude will converge, okay? So if you converge at any point, you must converge at the circle containing that point, right? So this is explained here, right? So the ROC consists of, Z equal to R times e to the j omega, for which this xn times r to the minus n has a Fourier transform, okay? So if this has a Fourier transform, then this converges, right? Then the Z transform converges for any point z with magnitude r and any value of omega, okay? All right, and the second property says that, okay, so what's different from the continuous time case is that in the continuous time case, we say that if you converge at any point, you must also converge at the line corresponding to that point. But in the discrete time case, we're sort of just folding this into a circle, right? Saying that if we converge at any point, we should converge at any point on the circle, okay? So if we converge at any point, we should converge at any point on the circle. All right. So the ROC does not contain any poles because, again, the value of x at the pole is infinity, right? And if xn is finite duration, then the ROC is the entire Z plane, right? Except possibly, except possibly at 0 or infinity, okay? So it could include the entire Z plane, but except for some exceptions at 0 or infinity, okay? So why do we have these exceptions at 0 or infinity? Okay. So because if you think about it, when you have a finite signal, your Z transform will look something like this. Right? When you have a finite signal, you're basically summing this over a finite region. Okay. Now suppose that n1 is greater than 0. Suppose n1 is greater than 0, meaning that the entire region is greater than 0. So if it's greater than 0, then you have all the terms that you have is z to the minus of some positive value. Okay? So in this case, if you plug 0 inside, it will go to infinity. right? If this n1 term is greater than 0, then, well, n1 doesn't have to be greater than 0, but at least if n2 is greater than 0, then you must have some term that is z to the minus of some positive value. So when you plug 0 inside, it will blow up, okay? So if n2 is greater than 0, then you should have a pole at 0, okay? So the region of convergence would not include 0. Now, similarly, if you have n1 less than 0, then this means that you have z to the minus of some negative value. So basically, z to a positive power. So for z to the positive power, if you plug infinity inside, then it will be infinity, right? So in that case, right, if n1 is less than 0, you have a pole at infinity, meaning that it does not converge at infinity, okay? So whether or not 0 or infinity is included in the ROC really depends on, the region that you're summing over, okay? So if n1 is greater or equal to 0, then ROC excludes 0. And when n2 is less or equal to 0, then ROC excludes infinity. Okay? Okay. Now, the next property refers to right-sided sequences. Okay, so suppose that xn is a right-sided sequence. Okay, is a right-sided sequence. So right-sided sequence is something like this, right? It only has non-zero values to the right of some n. Okay. So in this case, if you know that the circle z equal to r0 is in the ROC, meaning that this signal can be successfully suppressed by a decaying geometric series with value r0, right? So this means that the signal xn is successfully, suppressed by this series r0 to the power minus n. Then it must also be successfully suppressed by choosing a value of r0, by choosing a value of r that is greater than r0, right? Because if you choose a value of r greater than r0, then it will, decrease even faster, right? Suppressing xn even more. Okay? So this means that, right, if this absolute value of z equal to r0 is in the ROC, then all finite values of z for which the absolute value of z is greater than r0 will also be in the ROC, okay? And that corresponds to, the exterior of the circle beyond r0, okay? So in this case, the ROC is the exterior of a circle. Okay? Now, similarly, if you have a left-sided sequence, and you know that this circle is in the ROC, then picking any value of r less than r0 will also successfully suppress the signal on the left-hand side, okay? So if your signal is left-sided, then your region of convergence should be the interior of a circle, okay? All right? Now, what if you have a two-sided signal? Okay, what if you have a two-sided signal? So the same logic holds as in the continuous time case. When you have a two-sided signal, you can split this into a right-sided signal plus a left-sided signal. So a right-sided signal has ROC that is the exterior of some circle, and the left-sided signal is the interior of some circle. So when you add a left-sided signal with a right-sided signal, the overall region of convergence should be the intersection, which can either be a strip or non-existent, okay? All right, so for a two-sided signal, if you know that this circle is in the ROC, meaning that the ROC exists, then the ROC must be a ring that includes this circle, okay? And this is because you can split the two-sided signal into a right-sided signal, which has a ROC like this, and a left-sided signal, which has a ROC like this, and the intersection of these two will be this, okay? So this corresponds to, the right part, and this corresponds to the left part, right? And if you have xn equal to the left part plus the right part, you should have an ROC that is the intersection, okay? Okay. So maybe I should stop here. But what I'm going to do is okay. All right. So what I can do is that we can set our final exam to cover parts up to this, right? So basically, these are the exact same properties as before. Okay, so I can also go through this. This is saying the exact same thing, just that it should be bounded by the pole. Okay. So it's saying the same thing as this, except that it should be bounded by the pole, right? Okay. So anyway, we can set the final exam to cover, the parts up to this point. Okay. But we still have, I think, the last homework problem, which may use some properties, which may use some of these properties like time shifting and things like the convolution, So I'm going to post a video for this part, okay? But I believe you will be able to solve it even if you don't, look at the video, because all of this is the same as the continuous time case, okay? So we have a last homework problem that will use this convolution property, but I believe you already know it, right? Convolution in time is the multiplication in the Z domain. Okay. So I'm going to post the video. Okay. I'm going to post a video for the remaining of this chapter, but our final exam will go only up to this point. Okay? Is that clear? Okay. Yes, so we'll still have class next Wednesday, and I will complete the rest next Wednesday, but we will not cover that in the exam. Okay, our exam will only be up to this point. Okay? 这没有办法，对对对，没有第一次段考之前的就不，就是第一次段考之后的范围。对 ，OK。不过因为它都是互相 dependent 的嘛，所以你也很难不懂第一次段考的东西，就懂后面的东西。对。哇，有没有其他的问题？